Okay, good morning everyone. So we start our morning session, and our first speaker is Vershynina. We'll talk about measuring quantumness of the system through.
All right, thank you very much, and thank you for inviting me for this session. So I'm going to talk about coherence from two points of view, statical and dynamical, a little bit at the end. Just introduction what the dynamical resource theory is. So we'll start with various relative entropies. We find the coherence through this relative entropy of coherence, René, Thales, and others, and F coherence in particular, and the distillation of coherence. Can you distill a higher coherence state from a low coherence state? And I'll finish with just a quick overview of the dynamical resource theory of coherence. So we've seen this before. Quantum relative entropy is defined for two states. States are Hermitian. Trace 1 as a trace rho log rho minus rho log sigma if the supports are of rho is in sigma, otherwise it's infinity. So it's non-negative. Few properties. It is unitary invariant, meaning that noiseless quantum channels do not change the relative entropy. It is additive on tensor products, and one of the most important properties is the monotonicity of relative entropy under noisy quantum channels. And so if this n is a completely positive trace preserving map, meaning noisy channels, then the relative entropy decreasing, meaning it's harder to distinguish these states as they become more and more scrambled. In particular, we can take a partial trace as this channel. And, well, that's a topic of another talk. What happens in the case of equality? So if we do have an equality, in this inequality, Pat showed in 80s that there exists a recovery channel particularly for this channel and these two states. So for these two states and this channel is basically noiseless. You can recover from it for these particular two states. Okay, René relative entropy is a generalization of the classical René divergence. So for alpha not equal to 1, it's a log trace rho to the alpha sigma to the 1 minus alpha. In the limit, it approaches the previous omega k relative entropy. It is a part, well, you can view it as a part of a more general class of relative entropies called divergences or quasi-relative entropy. So if f is an operator convex function, which takes value 0 at 1, the quasi-relative entropy or divergence is a trace of f of the module operator applied to rho. So this is a module operator, left and right multiplication of A and B inverse. And if you know the spectral decomposition of rho and sigma, then you can just calculate this trace straightforward. Then the trace becomes lambdas. Lambdas here are from rho, f of all possible fractions mu from sigma, lambda from rho, and the overlap between these states. Now if you take the function logarithmic function, then you recover the original relative entropy.
Anna, may I ask a question?
Yes.
Just out of curiosity, have people also considered more general functions f of lambda j mu k? Right, you know, you have this very special lambda j f over mu k over lambda j. Does it make sense to consider more general functions as functions in two variables, in lambda and mu? Does that also lead to something reasonable?
Not that I've seen. I don't know.
But you also don't know that it doesn't work, right?
Yeah, I don't know.
Okay, that was my question, because I think
I don't know.
because in terms of functional calculus, right? I mean, why do you use this special relation? It's a fair question.
But this is because if you want it to be homogeneous, it has to be of this form.
Right, but do you have to? I mean, you know, we are generalizing and generalizing. Who the heck cares about homogeneous anymore, right? I'm just asking. I mean, I've seen other examples which might be interesting with honestly without two functions. But then I don't know whether they are still satisfy all the other rest.
Yes, yeah.
So sorry, yeah. just-
That's an interesting, I don't know. Right, so if we take the power function, normalized to make it operator convex, then this becomes what's called the Thales Q entropy. Again, it's a generalization of a classical one. It's a trace root to the q, sigma to the 1 minus q, so it's similar to what we've seen in Rene without the logarithm. So again, it's just normalized. And again, in the limit, it becomes the regular relative entropy. And the Rene relative entropy, it's a log of the Thales divergence. Oh, sorry, of the Thales divergence here. And there are many various definitions of quantum relative entropy. This is from some paper. All the connections between them. It's a whole zoo. But we're going to focus on just those. And the title of the talk is coherence, so let's talk about how we define coherence. So to define coherence, we fix a certain orthonormal basis on a system in a lab, and all states that are diagonal in that basis, they're called incoherent. So these are free states, something that is very easy to prepare. So again, remember, this is a prefixed basis, okay? I'm going to denote the set of incoherent states as a. Now, what maps are free? So what can we do with that system? So there are a few definitions. Any CPTP map has a Krauss representation, and the map is called incoherent operation or IO if for each of the Krauss map, it maps the whole set of incoherent states to the set of incoherent states. So it may not preserve each incoherent state, but still it is free. And any reasonable measure of coherence, it should satisfy, well, it is zero if and only if the state is free. It is what's called monotone, non-selective. It's just monotone under these free maps, right? Strong monotonicity, it is monotone if I know the outcome of the measurements, and it is convex. All right. Now, the last two properties, they follow the second one, so if you can show the last two, that implies the second one. Alternatively to the last two, you can add what's called C5, is the additivity on the subspace independent states. So if you take a direct sum, rho 1, rho 2, with some weights, so it's still a state, then it is additive.
Excuse me, what
Yes.
motivates this resource theory?
Huh?
What motivates this resource theory?
What
So you're
motiv-
defining a set of states and a set of operations that live in these states.
Right.
Is there any situation in the lab where you have this?
Well, right, so what do? You fix an orthonormal basis, right? So that is something that is easy to prepare in the lab. And these are your free states, so they don't have any cost on them.
Yeah, but then okay, suppose that one of the three operations that you're writing, for example, would be a permutation, right, of the basis.
Sure.
Okay. Suppose that you're in a lab and you can implement this permutation. How do you implement this? It's a unitary. How do you implement it? You switch on a Hamiltonian for some amount of time and then stop, and then just how you implement it. Suppose that you switch the same Hamiltonian for half the amount of time, then you will get coherence. So I cannot think of a single physical situation where you have this set of operations.
That's an interesting one, yeah. Well, we'll have to think about it, yeah. Yeah, something we can talk about.
So if you feel very weird about the word coherence and decoherence, welcome to the club. I mean, everybody sort of knows, but it's very, but your argument that is kind of, in flux. It really depends on your perspective, right? Half of the time, the most.
Yes. Well, I'm following the literature on the resource theory of coherence for a while, right? And the people, after like 10 years, people haven't proposed a single single experimental situation where you have this theory. And whenever they make experiments, right, I mean, to show like some feature of the result theory of coherence, they always instruct the experimentalists not to create coherence. So they cannot, yeah. It's poorly motivated, I think.
Well, it is dual sort of to the theory of entanglement.
No, mathematically I don't have any concern, right? I mean, and I agree that you can prove very, very non-trivial statements, right? I mean, it's more about what is this for.
All right. In that case, okay. Right, so I define this incoherent operations, right? You can restrict to other classes of operations and have another sort of a theory on that. So for example, the genuinely incoherent operations, the one that preserve each of the free states. Yeah. And it's interesting that the operation is genuinely incoherent, so it preserves each of the free states if and only if all of the Krauss operators are diagonal in that prefix basis for any representation of Krauss in the Krauss form. And then if the measure satisfies the first two, it's a measure of genuine coherence. It satisfies the three, then it's a genuine coherence monotone. So let me define the dephasing operator first, and then we'll talk about other possible free operations. So the dephasing operator, it just maps a state. It's a full matrix, right? And you just look only on the diagonal elements. So you just preserve the diagonal. Everything else is zero. Okay, so you just forget about the coherence there. And then the map is called strictly incoherent if for any Krauss operator it commutes, sort of, so to speak, with the dephasing operation. Okay. Every genuine incoherent operation that preserves states, it is a strictly incoherent operation. And another class is a dephasing incoherent operation if the full operation is commuting with the dephasing operation. And this is a larger class again. All right, so we have this inclusion. All of them in IO, of course, all of them are incoherent operations. All right, so the natural measure of coherence is the distance-based measure of coherence, similar to the entanglement theory, is just how far your state from the set of free states. And this measure of distance is by the relative entropy. Relative entropy, Rene relative entropy, Thales, any of that. And it was introduced in 14 for any distance, basically, and C1 is satisfied whenever the distance between the two states is zero, if and only if the states are the same. C2 is satisfied if D is monotone under noisy quantum channels. And C4 is satisfied whenever D is jointly convex. So the question is, when is C3 satisfied? Nobody knows. We don't know the condition on D for it to satisfy C3. So relative entropy of coherence, so let's just take relative entropy, right? It satisfies all of those properties, so we're good. It's a good measure. You can write it, in fact, which state minimizes this distance is exactly the dephased state. All right, and it actually turns out to be just the difference between the entropies. It's just the way you write it. And it satisfies all of those four properties, including C3, which you need to show separately. Okay. From here, the interesting application is that it is impossible to distill a higher coherent state from a lower coherent state via the genuine incoherent operation. So if only operations you have are genuine coherent operations, then it is impossible to create coherence in your state. So what does it mean to distill? So a state sigma can be distilled from a state rho with a certain rate if there exists an operation that can send a multiple of the states that you have to tau, and tau is close enough to the multiple of a state sigma and you take trace 1 as the distance. So the optimal rate at which the distillation is possible is the supremum of rule such R's and such protocols. So, okay, this is the trace norm. So this was shown in the 16 that it is not possible to distill a high coherence state from a low coherence state. And I just want to show the proof quickly to see what is used in that proof. So let's do it by contradiction. Suppose it is possible. Yeah, so suppose we do distill state sigma from a state rho, and sigma has more coherence. Yeah. So in particular, there exists a GI operation for any epsilon, such that, well, you map this the n copies of rho with lambda to some state, and that state is close to your sigma. So that means that there exists, so this is a separate result, which I'm not going to show the proof of, a separate result that this state is actually, you can get it from rho via the GI operations. Okay, so the copy n copies and then GI operation is in itself a GI operation. Okay. So what does it mean? It means that for any epsilon there exists a GI operation such that mapping rho becomes close to sigma. Okay. Now, this is important that we have a continuity for the entropy. Okay, so this is an old result, 2007, that if my two states are close to each other, then the entropies are also close to each other. Yes, and that bound, it's a binary entropy, so it goes to 0 when epsilon goes to 0. Okay. Alright. So the relative entropy of coherence, which is the difference between the entropies, right? It is also monotone because for this, the first term, the deltas, the dephasing operation, it's a CTP map. So if the states are close to each other, then the dephased state are also close to each other. And then I can use the continuity inequality here again. Alright, so this is going to be the difference between coherence, less or equal than 2 of this bound, h of epsilon, which goes to 0, right? Okay. So because the difference between lambda rho and sigma is small, we have this inequality as well. Alright. So again, this goes to 0 when epsilon goes to 0, and this is how we get the contradiction. Well, for any delta, it means that it is true that this bound is less than delta. For any delta, I can find this epsilon for G operation. So let's take the delta, the difference between, oh, there's no f's here, between the coherences. And our assumption at the beginning of the proof was that the coherence of sigma is larger than the coherence of rho. So this is positive. Let's take that. So the second result that we're going to use is that coherence is monotone under the GI operation. Okay, so we use the result of continuity and we're using the monotonicity here. Well, therefore delta, which is 1/2 of this one, is less or equal than 1/2 of the difference C coherence of sigma minus coherence of processed rho from the above inequality. Well, which is strictly less than that difference. Okay, so that inequality from here, and we get the contradiction. Delta is strictly less than the difference, however, it is greater than the difference, then that's a contradiction. So, again, for the proof we use two facts, the continuity of the entropy, yes, and the coherence was the difference of this entropy, so whatever entropy I'm using, I need that continuity, and I need monotonicity under the operations that are free. Alright, so let's talk about the Rene entropy of coherence. Yes. So we take the Rene entropy, that's the Rene relative entropy, as the distance between the state and the set of states. A second definition would be just like a second definition for the relative entropy. It was the difference between the entropies, right? Or so that's a Rene entropy, or it could be just the Rene relative entropy itself between the state and the dephased state. Yeah, so all three are the same for alpha equals 1 here. All three definitions are the same. So the first one, the distance-based, is a distance-based, so all of the previous results applied for any distance, and additionally, these guys in 15 showed that it does not satisfy C3. C2 is satisfied under any incoherent operations, but it does not satisfy C3. The second one was considered in 21. It satisfies C1. Everybody satisfies C1. C2 is satisfied under the GIO operations, and it does not satisfy C5, which was equivalent to 3 and 4. Yeah? So C3 is satisfied, so I showed that it does satisfy under GIO on pure states, and additionally the equality is satisfied in C3 under GI in 2 and 3 dimensions only. And the third definition satisfies the second one, the monotonicity under DIO operations. Okay, now the question is, as I said, when alpha is equal to 1, all of these three definitions are the same. Why are they not the same here? Huh? And the third one, it does not equal to the second one or the first one, because the minimum state that achieves this distance, right? It was calculated precisely. That's the state that minimizes that distance. So you would get the first one and the third one. This has to be this alpha, not just delta, the phase operation, but exactly this delta alpha. All right, so the first one, yes, is equal to this one. You can calculate it precisely. Similar questions for the Thales entropy, right? So just natural. You can consider the three definitions for the Thales relative entropy. Again, just the difference between the entropies. The first one does not satisfy C3. Even it's distance-based, but it's not satisfied C3. It satisfies a modified version because of those powers you have there flying around. The second one satisfies a modified version of C5, so it does not satisfy C5 in general, but again, with these powers, it satisfies C5. All right, so the question is, well, why are we considering it in such a form, right, as the difference between the entropies? It's because for the relative entropy, this delta rho was the smallest state, the closest state to rho. So let's take instead the closest state in this difference. So if I put here delta alpha, this is the closest state to rho, and I consider the difference in entropies here. So that is the closest incoherent state. So we have that equality. You just can calculate it straightforward, and it's the first one, but then you have this trace of rho alpha and additional something. So it does not equal to the first one. It's greater or equal than the first one for alpha between 0 and 1. When alpha is larger, it is less or equal than the first one. If you similarly define for the Rene entropy, yes, take the Rene entropy, this is the closest incoherent state. Well, it turns out it's the same one. We already consider that that's the first one. In fact, all of these two equations hold for the Rene entropy that they were holding for the relative entropy, for the regular one. Right? It's just kind of funny. All right, so not getting anything from the Rene entropy, looking at the Thales entropy. All right, so Well, it is zero only if the state is free. It is invariant under diagonal unitaries, right? So the unitaries that are diagonal in that perfect basis that we fixed at the beginning. The GIOs in 2 and 3 dimensions can be written as the convex mixture of such unitaries, but it is not monotone under GIO. Right? However, it reaches equality in a strong monotonicity for convex mixtures of diagonal unitaries, in particular GIO in 2 and 3 dimensions. It's not monotone under all unitaries, which is pretty easy to show. It is monotone under alpha GIO, so those that commute with delta alpha. So the GIOs, they commute with the regular dephasing. If they commute with delta alpha operation, then it is monotone. Which operations do commute with delta alpha? Well, in particular diagonal unitaries, right? But the question is, are there any other maps? I don't know.
Can I ask you one more question?
Yeah.
Sorry. Have you ever thought of looking at CT alpha of rho to the 1 over alpha?
CT alpha of
Rho 1 over alpha. We're leaving the, because, you know, this alpha normal, if you do it in infinite dimension, you know, if rho is state, rho 1 over alpha would be in the corresponding L1 over alpha space or alpha. So somehow I was asking, what if you consider CT alpha of rho 1 over alpha, whether that behaves...
power 1 over alpha?
Right.
Yes. Yes.
That would somehow looks better.
Yes. Yes.
And
yes,
what
there.
did you see what properties that have? I will probably lose some of the other properties, but
I can look that up because there's so many definitions with
Yeah.
all of these powers. There are several papers with.
if you go one page back, right,
Yes.
or maybe where you have these formula
Yeah.
with right. So if you
Yeah,
apply
yeah.
this to 1 over alpha, you see then it's trace of rho again.
Yes. Yes.
And if you do n of rho 1 over alpha, that is exactly the right one.
Yes.
So somehow you should do CT alpha of rho 1 over alpha.
Yes. Yes. And I'm saying, yeah. It is done. As
Better behaved.
Yes. Yes. It is. Yes. It is a good measure.
Yeah.
And I'm saying, I mean, there are so many definitions with all of these powers, 1 over alpha there, or in this delta alpha, you can put the power outside, or you put the power inside, or the power inside and the outside.
Sure, but in infinite
Yeah.
dimension, where if you have a trace where you only control trace of rho, trace rho to the alpha might be unbounded,
Sure.
and then this makes just no sense whatsoever.
Right.
So that's why I'm suggesting
Yeah.
to consider that
Yeah.
one as well.
Yeah. Yeah. Yeah.
Maybe you already know all the results anyway, but
Yeah. That's right. Okay. Right. Right, so as I said, it's monotone under all unitaries. That's a very quick something to check, because if it is monotone under all unitaries, it must be invariant under all unitaries, because you can go back and forth with these unitaries. So the inequality can go back and forth, so it must be invariant. So you just check it, and you're done. So remember, in that distillation process, we needed the continuity of the coherence, right? So here, two results for different alphas. For the Thales entropy and for the Rene entropy, the continuity of the coherence, and the right-hand side, it goes it goes to 0 when epsilon goes to 0. So it is a good bound. And the quick idea of the proof for the Thales entropy, for example, it doesn't matter which one, but for example for the Thales. So what do? Well, let's consider the overlaps here of my states, rho and sigma, which are pure states, with the prefix basis. Then the coherence can be written as these sums, and now we're just going to have to open up these sums a little bit. So I can write it as a trace of the function, which is 1 over alpha, of the dephased operator. So dephased is going to give me this size, right? So that's the dephased operator. Then you take it to the 1 over alpha. take the trace and then the whole stuff to the power of negative alpha. Alright, so the trace norm is monotone, so the states are close to each other. This means that the phase states are also close to each other. Right? So if these states are close to each other, then the trace of the F, so the F cannot map them too far if it's a nice map. So it maps them close to each other. And why is this? So this F is again for this one. H is calculated for this function, and it was shown in 2021 that well, for if you define the entropy as a trace of any function g of rho, the convex function, then it is well, we have the continuity here, the continuous bound, that the difference of the entropys is less or equal than all of that. So that is my h calculated for this function. Okay. And it's also shown not only for states, rho and sigma, trace one, but also non-normalized, not unit trace matrices. Alright, so for that function, it's convex. We have the majorization of the sequences 1 over d for psi and psi and xi. So by Schur concavity, those sums are bounded below by d to some power. That's good. And now we can use the monotone, the mean value theorem, that something to the power 1 minus negative alpha minus something to the power negative alpha, those two are close to each other, so again you cannot go too far. This is equal to the derivative of this function at some point, I don't know that point exactly, minus the difference between whatever's inside. So whatever's inside there, the difference is bounded. Alright, so we just get the derivative of the function g, which is that power negative alpha. And at the same time, if you calculate the largest possible basically difference, the derivative of this derivative, it's going to be at the point d to the power, that's the smallest one. And again, by the mean value theorem, there exists the point, blah blah blah, and I can bound this by this difference and calculate this difference just precisely for my function. And you do the same for the Rene entropy, but instead of the power 1 over alpha negative alpha there, you just change it to log. So minus alpha to the log. All right. So the last generalization is the F entropy, right? So I can take that in my relative entropy definition. So this was the relative entropy, which is equal to the entropy of the difference. Now let's replace this with the F entropy. Yes? So that's the second sort of approach. Instead of looking at the states, now we're looking at the entropy. So for any operator convex function, as I showed, this was the F entropy, right? The trace of the F of the modulo operator. So let's define the F entropy as the relative entropy between state and the identity, or normalized identity. Either way, it doesn't matter. So that's how you would get the regular entropy from the relative entropy. Alright, so this entropy is non-negative. It is 0 in pure states, as you would expect, concave and rho. It behaves nicely invariant under unitaries, non-decreasing under unital, unital CT, CP, TP maps. And we have the continuity again. But this is straightforward from that Pinellas paper. Alright, so it follows directly from this result, but you just modify it for whatever function you have. Okay, so this is my H epsilon, which goes to 0. When epsilon goes to 0. And from the entropy, F entropy, we can define the coherence as the difference. Yes? And if you know the eigenvalues of rho and the diagonal elements, this is how it's gonna look. So remember in the proof we had this f, but the f was 1 over alpha, but now we can just take any operator on this function here. So it is a negative 0 on incoherent states. It's upper bounded by corresponding bounds. Monotone on the GIO, which is what we needed for the distillation protocol. We needed the continuity and we needed the monotonicity. It's saturated monotonicity for convex mixtures of diagonal unitaries, in particular GIO in 2 and 3 dimensions. And it's only monotone on the GIO in any finite dimension for any pure states. All right? And we do have the continuity as again. All right, so we do have this distillation result similar to what was done before. It's not possible to distill high coherent state from the low coherent state via this GI operations. All right, and now I just want to go to the dynamic resource theory. So there are no new results here. Just want to introduce this topic, and maybe somebody knows more than I do about it. It's just something I'm interested in right now. So for the static one, which is on the left, dynamic on the right. So we fix the d-dimensional Hilbert space, right? This is the state of space, the space of states. And on the right-hand side, we fix the bounded linear operator space. Okay. Now, what do we have on the left? These are the states. We have objects, free objects, or just any objects. They are states, trace, one positive operator. On the right, we have the channels. Yes. Completely positive trace preserving that. Okay. Now, the relative entropy, the distance between these two objects is defined by relative entropy, whichever the definition you like. On the right, we also have the relative entropy between channels. The relative entropy between channels is defined as the supremum of the relative entropy. So you apply each of this channel to the state rho, but you increase this rho to include the reference system to make sure it's monotone and everything. So it's technically it's the identity there. For each of the channels, you tensor it with the identity and apply it to the bigger state rho on the reference system and the original one. But you don't need to take any possible rows here. You can just take the, by purification, only pure ones. The dimension of R is the dimension of A, and all of that. Okay, entropy. So we have the entropy for the states, trace rho log rho. It also could be written as log D minus the relative entropy between the state and the maximally mixed state. So in a similar fashion, the entropy of a channel was also defined as the log D minus the relative entropy between your channel and the completely depolarizing channel. So this channel that maps everything to the maximally mixed state, to a D. All right, so we have the relative entropy, we have the entropy. So what are the free objects, right? This is the resource theory, so we need to have the free objects here. All right, so the free objects for the states, how do we get them? Well, we fix the orthonormal basis of the Hilbert space. That's E. Now, we'll look at the orthonormal basis of the bounded linear maps, which is this IJs, right? And the free incoherent states are the diagonal, or the convex mixture of these diagonal ones, XJJs. So this is a subset of classical states. Okay. Now we do have the completely dephasing operator, which is going to be helpful to define the free operations. And the free operations with the Krauss possibly representation. So the first one, they preserve the set of incoherent states. The second one, each of the Krauss operations preserve the set. DIO, the commutes with the dephasing operator. SIO, each of the Krauss one commutes with the dephasing operator, and GIO is each of the free states is invariant. Yeah. All right. Then we have the inclusion from down to the to up. All right. So let's look at the corresponding what we have here. So free incoherent states. What are the free channels? One of the possible ways to look at it is just free classical channel. Any classical channels, they are free. And this was done in 2020. So the classical channels, they are the one that stay invariant under sandwiching between the dephasing operator, this one. All right, another possible set of free operations, so free channels, is a detection incoherent operation. So the sandwich one, so if I map my state to a classical one, then do my state, and then map it again to the classical one, it's the same one, so as just doing the channel and then doing the classical one. So that was done in 19. Creation incoherent, this is actually correspond to exactly this one, MIO. You switch the order. First you map it to the classical one, and then you do the channel, and it is already classical. So if you map it to classical, you're not going to do anything. It's already classical. Detection creation incoherent, your channel commutes with the dephasing operator. This corresponds to this one. It commutes with the dephasing. It's exactly the same one. All right, so these are possible choices for free channels. That's one approach. There is another approach in 18. Well, it's sort of another, sort of like a subset of what we've done. The detection incoherent measurement. So now we're only looking at the measurements. So the channel is written as you're measuring the row with the m's. M's are positive, sum up to 1. Everything is fine here. But the result is just this psi case, this psi k. These are not the prefix bases, just any ones. All right. So these are detection incoherent, creation incoherent measurement. The result must be classical. Yeah. So these psi's are actually the fixed bases, and detection creation incoherent if you also have the measurements in the classical bases, in the fixed bases here. All right, so that was in 18, another setup, and there's another one. So let's look at this way. So we fixed the bases in the B of H, right? And then we took the diagonal ones only. We already have the bases in the super channels, in the B of H, right? These operations, these channels, you calculate the overlap, and you basically change your bases, right? From K to L, you change it to from I and J to K to L. So the free channels could be looked at if my indices are I and K are the same. So you look only at the diagonal ones, and you change them in that basis to the diagonal ones. With the normalization, one of this normalization is necessary to make sure it's trace preserving. The second one, you may have it, you may not have it. All right, so if I calculate what this n is, right, you can write it in the form of the measurement, coherent measurement, with MKs in this form. So it's a subset of what we had before. So this is a subset of classical unital channels. Unital comes from this sum. Now, to define the other ones, we do need the completely dephasing now, the super operator, right? So we define this one with the completely dephasing operator, but I'm talking now about the free, not just the channels, but free super channels, right? So For the static one, we needed the free states and free operations on them. Now we're talking about the free channels and free operations on them, which are free superchannels, right? So what are the free superchannels? So the completed dephasing operator, again, that was one definition. One definition is to look at the sandwiched channel with the dephasing operator. Okay. Then for any unital channel, it maps any unital channel to a set of free channels. All right. And for any free channel, it just preserves that channel. Okay. And only the free channels are preserved. Okay. All right. Now, the dephasing operator, right? This dephasing operator can be written as the sum of this xjj, which is the part of the basis rho xjj, and that sort of like motivates that form for the dephasing super operator. And another definition, again, more motivation from this form. If you look at this form, yes, you look at the part of the basis and the part of a basis. So this is the those operations theta that we have upstairs there. So if I calculate what is this one exactly, this becomes, so this is the overlap with rho, overlap with n on the classical, just the projection there, and it's of course must be a classical state at the end. Here, for this one, it's similar, but now you switch in this ion case. All right. That's the only difference. All right. For unital channel, this delta 2, it becomes a free channel. It maps any unital channel to a set of free channel. So the unital channel is not a big restriction, because the unital channels, they don't create any coherence, so that's natural to consider only these channels. And delta 2 preserves the set of free channels like those ones. All right, so free super operations. What are the possible choices for free super operations? So corresponding to MIO, vehicle, MIC, the operations that preserve the set of free channels, right, natural ones. In the paper that considered it, they considered only classical channels, the whole set of classical channels, and it showed that this happens if and only if so if you sandwich it with the dephasing operator, it's the same one. It's going to be the classical at the end if you just do the dephasing and the channel. Corresponding to the DIO, the operation that commutes with this super operator, right, complete the dephasing super operator. Now if you write the super operation as the sum of rank 1 tree matrices, then corresponding to AIO, you can just consider the ones in a similar form as this one, but for each of these lambda k's. And corresponding to SIO, the ones that commute with the super dephasing operator. So this was done in 2020. Well, naturally, you can consider the channels that preserve each of the free channels. For whatever channels you consider there. Oh, this has to be N in C. So here are the few questions that I have. If you have a channel that preserves all of the free states, does it commute with the dephasing super operator in the first or second definition? Because here we have this set is a subset of all of these, right? So channels that preserve the states, they do commute with this delta. So the similar question is there. Or if this delta or delta 2 preserves the channel, is it a free channel? So are there any examples that it preserves something but it's not a free channel? All right, so these were the possible definitions. There's another way to look at the free superoperators, is to notice that every free any super channel can be written as in the following form. So there exist two channels M and K on the outside. So you first tensor your channel with some additional one, right? And you do the composition with two other channels. So in this way, you can look at the free operations. The free operations are such that these new channels M and K are free in whatever previous definitions you wanted. It could be detection, creation, incoherent, or just any free states free set that you want to consider. So this was done in 18. And then the coherence of a state, this is how we defined through the relative entropy, right? So for any measure of coherence of the channel, well, it must be non-negative, 0 for all free channels, or you can say if and only if it's a free channel. It must be monotone for any free super channels, and possibly convex. Some papers consider it a requirement, some not. So in 18, Jan considered the coherence of a channel as the minimum distance between the channel and the set of free channels, which was the detection, creation, coherent. 3 choices there, with the relative entropy between channels. So here's the relative entropy between channels. You can also consider trace 1 norm or some sub-multiplicative norm with respect to the tensor product, or trace 1 norm. And instead of the just relative entropy, you have to compose it with the phase operator here. But here they considered only the detection incoherent maps as the free channel. All right, and in 20, they considered the relative entropy between a state and the dephase, or between the channel and the sort of like dephase channel, similar to what we had for the channels there, for the states, S rho and the dephase state. All right, so this was monotone on the disk because disk is commuting with the superoperator. So it's not, it's very straightforward there. Here's the proposal. Well, we can define the coherence with the second definition of the phase in superoperator. So that was the first one, this one the second one. We can also define the coherence as the difference between entropies. We have the entropy of a channel, so we can define it as the difference of the entropies of the channel, which is the difference of the relative entropies with the completely randomizing channel. And of course you can take the delta or delta 2, whichever you like. However, there are some of these definitions, some properties you can easily show, some properties much harder, and a lot of those properties, like for example, the first one, if this is a 0 one, right, then your state is free, so that's good. But if your state is free, why is that a 0 one, right? Or for the last two, if I have the equality, what I need is the recovery condition. We had a recovery condition for the relative entropy, but I don't know, there is a monotonicity for the relative entropy of the channels, but Does anybody know any recovery condition for the equality case? Is there some super operations that's going to recover these channels? I don't know. So that would be interesting to see. And in general, you have a very simple result. If you have some super channel, right? So this delta, whatever your definition of delta is, the super dephasing one, but it must satisfy a property that it is free for any channel, right? So this one is free, and it preserves the free channels, whatever your free channels are. So you have two freedoms here, whatever free channels here, and whatever definition of delta, okay? Then the free super channels are the ones that commute with this delta, like disk. Then if you define the coherence as the relative entropy between the state and the dephased one, then it satisfies all the properties. It's zero if and only if the channel is free. It's monotone under these free super channels, the one that commute, and it is convex because the relative entropy is convex. Okay, but if you don't have all of these conditions, then it becomes a little bit harder. So that's why the previous definition with the delta worked, because all of these conditions were satisfied. All right, thank you. Let me stop here.